Okay, good. So homework 6 still is on in action, right? On Tuesday, Thursday midnight, and a new homework will be given on Wednesday. As I said last week, this homework 7 will have a longer deadline because of the exam, like 2 more days than usual. Yeah, other than that, I mean, next week the exam is on Wednesday, and we'll do again a review on, but next week we'll do it, so we don't not need to talk about it now. And there will be a sample exam posted this week sometime, like towards, I think I will post it on Friday. So then, no, not even that, no. The sample exam will be posted next week, like on Monday. So then you can just work on it. And on Wednesday, I'll be solving the sample exam. Okay. So, but before that, of course, we need to take care of some business. Last time we finished mathematical induction, like we learned a new proof technique, proof by induction, right? Based on mathematical induction. Of course, if you had a chance to look at chapter 5, it's a big chapter. There are lots of other versions and various issues about induction in general. But we just looked at the first section, sort of, right? So please review those notes well that we discussed last time, right? And expect a question in the exam about proof by induction, FYI. Today, we are going to look at a new topic, which is chapter 6. There you will see counting. So chapter 8. In mathematics, of course, they call it combinatorics. Combinatorics is the branch of math which deals with counting in general. Definitely a very fundamental topic, and you'll see we computer scientists need to develop some insight about this topic. So when we say counting, a non-mathematician and non-computer scientist would probably imagine what we call normally enumeration. Let's say I have, I don't know, like a bunch of objects. So if I tell you how many items are there here, so you would count, right? 1, 2, 3, 4, 5, and 6, and then conclude that, yeah, there are 6 items over there. If I ask more, you could tell me, yeah, there is a square, there is etc. But simply, we enumerated them, and natural numbers were handy over there, right? Like we used natural numbers to enumerate these things. But counting, of course, is more than that. There are, like, this is a non-trivial instance of the problem. How about the following? If I ask you the number of students registered to UT Dallas, again, like you can, in theory, you can count like you did here, right? First student, second student, etc. And then you would stop at a number like 30,500 something. But things can even get a bit ugly here. For instance, the number of female students at UTD campus right now. This is a counting problem too, right? Legitimate. We know there is a first student, female student, who is here at this point, and there is a last student. But what is that last number? In theory, it is something finite. It shouldn't be that hard. How are we gonna find it? So that's also counting. Yes, in practice, we are aware that finding that number, like right, it's a bit since it has more information, getting involved. It won't be possible to find the number of female students at UTD campus at a specific moment. Yeah, maybe some of you can say, okay, they have cell phones, They are registered, so with the help of the operators, we can locate them and locate the female students, etc. But you see, things are getting uglier and more energy, more effort is needed for such a simple thing. So I hope that this counting, yeah, fine, this is counting, but there are also other ways of counting. Or just another example which came to my mind. Take the US map. Pick two cities, Dallas versus say what, I don't know, New York City. How many routes are there from Dallas to New York City? I mean, yeah, we know a few, let's say, if I want to drive, right, up there, there are a bunch of, mostly I agree with you that many people will pick a few main highways, etc., and then they will, there are a bunch of ways which are used in general. However, right, it's not 4 or 5. I have to remind you that the country is all connected. So a route which first leads to Seattle, then goes to New York City should also be counted. So there are, you see, like counting sometimes it requires us to be very careful. We can't simply say, okay, yeah, I know from Houston to Dallas, for instance, 45 or 20, 45, right? But it's not the only way, right? There are many other routes between Houston and Dallas, for instance. So yeah, quite a intriguing topic. Easy instances are funny, but there are many ugly instances too. Very hard to count. And also, like, I have to remind you that, so if you cannot count, you cannot understand probability either. If you can't do probability, probably you won't be able to do many fancy and popular branches of CS nowadays, let's say machine learning, linear algebra, etc., deep neural networks. They all require you to understand, have some sense of probability. But probability requires to know, requires counting well. And counting well requires, like sets. Sets require logic. So everything is connected. Okay. So I hope that the motivation is clear. Like it's all around the real world again. So nothing, comes into our class unless they become very, ubiquitous in daily life. So I will not talk about this motivational part anymore. I'm going to talk about, say, math. We are going to look at now. We are going to learn how to count rigorously. Whether it's a simple instance or hard instance, there are basic rules. There is a basic theory developed by mathematicians over the last 300 years or so. All right, and we want to count correctly. We want to also, like let's say we want to first count, and then we want to make sure that we count it correctly. So these are the two main tasks. All right, but this is all done by making use of some basic counting rules. All right, so this class, in this session, we are going to cover 4 of them: the product rule, the sum rule, the subtraction rule, and the division rule. And then after that, next class, we are going to look at more involved ideas. But all the combinatorics or counting issue relies on these 4 basic rules that we will discuss today. The rest is just built on top of these basic rules. Okay, let me start first with the product rule. Okay, so it says I'll write the statement of it first. If a procedure can be broken down to a sequence of, two tasks, such that there are n sub 1 ways to perform the first task. And there are n sub 2 ways to perform the second task. Then there are, let's say, n1 times n2 ways to perform the procedure. So first of all, do we all see that this is an P implies Q statement, right? There is a P, right? And there is a Q. Are we clear about this? This is a P implies Q statement of the, the form of this statement. Yeah, it's long, but still it's a P implies Q. It's a conditional statement. And it tells us, okay, you want to imagine perform a task, like you want to run a procedure. A procedure like an algorithm, right? But a generic format of algorithm. Has a beginning and an end. So imagine this procedure involves a sequence of 2 tasks, task 1, task 2. First, it says you do task 1, and you can do it n1 ways, and you can do the second task in n2 ways. Then the overall procedure can be done n1 times n2 ways. So a very basic, a very classic example of this rule is this. Imagine there is a city A, and there is a city B, like in Dallas. So we just focus on, let's say, there is a city in between. I would call it I. And from A to I, you want to go from A to B, okay? A to I, imagine you go in 2 ways. There are only 2 routes. Somehow you counted and you found there are 2 routes. And there are 3 routes from I to B. So then in total, okay, this is 2, this is 3. Then from A to B, there are 2 times 3, 6 ways. This is like the hello world example of this topic. Very classic. In every book you see it, a variant of it. But an important fact is, what is the procedure? What is the thing that you want to achieve? You want to go from A to B. So this idea tells us, okay, to go from A to B, you need to go first to A, I. Then from I, you should go to B. So there is a first task and a second task. Right? And then just as the formula says, you are done. In general, a procedure can be broken down to K tasks with, let's say, n1, n2 dot, and k ways to be performed. Then, right, procedure can be done or achieved, can be completed in n1 times n2 times that, and k ways. So we just generalize it. A procedure doesn't always have to be broken down to only 2 tasks. It can be as many as, I don't know, arbitrarily many. So with the help of these 2 basic definitions, let's say remarks, so we can just say, okay, how about this example? Imagine you want to write down the number of bit strings of length 6. Number of well, what is a bit string? Anybody remembers? Yes? Yeah, like zeros and ones, right? In a bit string, there'll be only zeros and ones in any order that you can imagine. So how many, imagine I want to focus, I want to calculate or count the bit strings of length 1. Oh, length 6, sorry. So that's how you will be thinking, okay, to write down a bit string of length 6, first you need to write a first bit, then a second bit, and the third bit, 4th, 5th, 6th. Naturally, right? Obviously. Everybody agrees with me on that. So how many, if I want to write the first bit, how many options do I have? A bit is 0 or 1. So it can be 2, right? Okay, I want to write now the second bit. Again, I have only 2 options. And it doesn't rely on the first one at all, right? Just I'm just writing, right, in these are the positions, and for each position, I'm just showing the number of options that I have. But then, according to the product rule, I have 2 times 2 times 2 times. Right, bit strings that are available to me. Because I can write 2 to the 6 different bit strings. The product rule tells me that. Of length 6, of course. Right? Each of these bit strings that I say here are different than each other. Not less, more. Exactly that many. Right? Because it says, okay, if you can do the first task in this many ways, second this many ways, and so on, then the overall task can be achieved in this many ways. Production rule, the product rule, multiplication rule, that's it. Okay, how about then, I think, did we have an exercise? Okay, we have an exercise 16. So then we can say number of bit strings of length n, right, will be, again, with the same idea, right? We can just, for any n, you know what it should be. Okay, let's just do a little bit more. Imagine we want to calculate the number of possible license plates we can write. After all, we see we are counting. So I want to count the license plates that I can write according to the template that we have in US. 3 capital letters followed by 4 digits, right? So number of US license plates. I mean, of course, that are possible, that are I think possible to write. So the format is this, right? There can be some X's, let's say some letters, and some digits. But now, as you see, counting, this teaches us one issue. Counting needs us to know what we are playing with. Okay, format first, we took care of it, we all agree. And how many capital letters are there? Let's say the first task, right? This is a task of 7 steps. First step is to pick a capital letter. So if you don't know English, and if you don't know that US people use English alphabet, you can't solve this, right? Some basic facts, So how many? It's 26, right? And again, for the second position, there is no reliance on the first one. Again, 26. 26. How many digits are there? Again, this time you need to know the number system. So in the usual number system that we use, we have 10 digits, right? 0, 1, 2, till 9. So here, 10 options, 10 options, 10 options. As you see, I don't have any restriction. Like I don't say something like, oh, the first and the third digits should be different. We don't say anything like that. Just without any condition, that's how we count. So then, as a result, we have 26, 10 to the 4 available plates. I don't know if is this too big enough? How are they dealing then? Because, oh no, you know what? It's enough. Because there is also at top of, there is another bit, right? Here it says, for instance, TX. So Texas, right? Like the same plate number can be used in different states because on top of the plate, it writes the state. But then they have enough because this doesn't look too much to me. I mean, this is 10,000. This is something, and for God's sake, in Texas, we have 29 million people, and almost everyone has one car. So may not be enough, but it's enough because this is just for one state, and then another state will have this many numbers for themselves. So, so we could make it maybe 50 times, but you get the idea, right? Like how many in general you can write down. Okay, just let's count functions. Another example. So let me write here. A number of functions from a set A to a set B. And let's say the cardinality of A is M. Cardinality of B is N. Okay. So here we need to know how functions act, right? Definition of function has to be known. So there are these M elements here and N. A function takes an element from the domain and maps it to an element in range, but exactly one element, right? Unique. It doesn't map like, you know, this element does not go to 2 elements, just it has to go. That was the function, the essence of a function, right? It's specific, something determines. So, okay, there are n elements here. Let me have, a function also should do this for every element in the domain. So writing down a function is like an m-step operation, right? M-step procedure. So to be able to define a function, then I will take the first element and map it to something. Take a second element and map it to something in the range, and so on and so on, until I'm done with the last one. So looks like I have this m-step. Clear, right? Like if I were to ask you, also this teaches us something like, imagine I want you to write a program which defines a function given domain and range. That's how we would proceed. You would take every element here and figure out something to do in the range, right? Map it. Good, the first task is clear, right? We understand. Procedure of defining a function, right, has this m steps because there are m elements in the domain. Okay, first element can be mapped to any one of these n elements, right? It would be okay, it would be a legitimate function. Second element could also be mapped to any one of these n elements. There is no restriction, right? Makes sense? And the third one, same again. Function definition would satisfy any one of them, exactly one of them. And there are n possible ways. And it keeps going on. But looks like the first task, right, defining a function, had this m tasks. The first task could be done in n ways. The second task, which is mapping the second element to a unique element, can be done in n ways, and so on and so on. Looks like the total number of functions that we can define then be n to the m. Make sense? Right? So we could define n to the m different functions, because a procedure of defining a function can be done in n to the m different ways. That's the gist. Okay, so let's solve element example. How many different ways are there to define one-to-one functions? From A to B, again, with the same, like M and N. All right, so the task of defining a one-to-one function. So let me write this. Okay, again, it's an M step operation. Definitely, that's for sure, like in the previous case. Now we have to be careful. There is a restriction. Remember, one-to-oneness requires us not to map two elements to the same function, right? We don't want something like this. So not one-to-one. Every element should go to a separate, like it should be. Okay, so then first element could be mapped to any one of n available elements currently, right? In the next step, the one that we picked in the first step cannot be involved anymore. So the second element then could be mapped to any one of remaining n-1 elements. Right now, one-to-oneness is still preserved. Next, n-2, and the last element in A, could be mapped to n-m-1 of any one available elements. So then, as a result, we will have n times n-1 times n-2 times n plus 1. So that's the way of counting number of different one-to-one functions from a set A to a set B. Yeah. I don't know what factorial means at this point. We didn't learn it. Yes, true. However, we don't know yet, right? We didn't define it. Remember, yeah, good math is definition oriented. You have to define what factorial means. It relates to permutation. You have to define what permutation means. So we will define it probably Wednesday or Monday next week. But yeah, everything in a hierarchical manner, okay? Yeah, true, actually, that's what we would do. But we don't know officially yet. I don't know where you learned it. Okay, so good. Then exercise 17. number of onto functions from A to B, right? Cardinality is M, cardinality is N. Okay, so something like, what else? Or how about this? You can count functions, then you can count the relations too. Number of relations from or between A to B. Well, I mean, you may not need to count for that. The reason is because of the definition. A relation was a subset of the Cartesian product, right? Like between A and B, A cross B, for instance. A relation from A to B is a subset of Cartesian product A cross B. But how many subsets does a set have in general? So from that you can solve it, but also you can solve it thinking like this way, by applying the product rule. Okay. Okay, let's just look at now the next counting rule, which is the sum rule. So if a task can be done in, let's say, either one of and one ways, or one of and two ways, where those two sets of ways are disjoint, then the task can be done in n1 plus n2 different ways. So, okay, I have an easy example for this and relevant to our life. So this is not same as dividing into sequence as you see. It's like, I mean, you don't do something first, then another thing first. Not that nature. That was product rule. Very handy. Let's put it aside. Here, imagine like you want to elect the president. We have to do this like every 4 years. So election of, for instance, US presidents. I mean, of course, there are many technicalities here, but normally you have two sets. Familiar set, right? And sets of candidates, let's say. Each party, right? Well, actually, yeah, I'm simplifying. I know that when you look at an official ballot, like there are 6 or 7 sets in general. Some parties, but we never hear them or their voice, like they are rarely heard. But we hear these two noise-making parties all the time, right? Like everywhere they are. So in simplified world, the two sets, there are two sets of candidates. But at the beginning of campaign, right? Last time I think this set had 16 candidates, then slowly it went down to 1. And the other set had 1 or 2, but then it just went down to 1. So at the beginning, right, when all this drama starts, let's say the red set has N1 candidates, and the other set has N2 candidates, possible candidates, or candidates for candidacy. right? That has a technical name, but I always forget that. So then people in US would know that one of these and 1 plus and 2 candidates for candidacy will be president at the end of the marathon. Isn't it true? And imagine, like, of course, we make an assumption here saying that a person cannot be a candidate in both sets, right? Like, no person becomes the candidate of both Democrats and Republicans, for instance. Of course, in some countries, you'll see that a candidate becomes a candidate from two parties because they coalesce, right? They do coalitions. But here, generally, that's the situation, like any possible ways to elect president. Makes sense, right? So that's a very simple application of the sum rule. And 1 and 2 candidates from each side, and at the end, one of them becomes president. All right. How about a more, let's say, math or CS-oriented example? Imagine we want to count the number of passwords satisfying the properties below. For instance, each password should be from 6 to 8 digits, or 6 to 8 characters, sorry. At least 6, at most 8. Of course, it's almost immediate, like a very weak password it would be, I guess. And each character is either an uppercase letter or a digit. And must contain at least one digit. Right? These are the properties of a valid password. And we want to count the number of passwords that satisfy these conditions. All right, so here, okay, we will apply both counting and, sum and product rule. But first, we should start with the sum rule. Focus on here, please. So how many different, like, okay, there will be a bunch of 6, the passwords that has length 6. And there will be a number of passwords with 7 characters and 8 characters. If P is the number of passwords that we are seeking for, then I can see it as like P6, which is the number of 6 character passwords satisfying the conditions, P7 and P8. So that's where, like, okay, the password that you can pick can be from here, here, or here. So there are this many different passwords available. We didn't yet figure out what these are. We will do this by using the product rule. So the first step, but you see, if you cannot see the sum rule in action, you won't be able to proceed, or it would get complicated, let's say. So knowing which rule or seeing the instance or application of the rule for any given problem plays a critical role. It simplifies the job a lot. If you jump into applying, let's say, product rule here, you might get lost. So let's calculate P6. Okay. So for that, it says, okay, either an uppercase digit or a character. So how many, let's say, number of passwords of length 6. Like this one I'm counting only, okay? Well, I have to pick 6 characters. So no, I forget this for a moment. I'll be careful, but for now. Well, there are 26 uppercase letters and 10 digits. So then the first character can be any one of these 36, right? And the second character, same, 36. So we have 36 to the 6 passwords without any condition that we can write down. Make sense? Length condition, except the length, that's it. But I don't yet consider this last, I will take care of it next step. Well, then, similarly, we have 36 to the 7 and 36 to the 8 for lengths 7 and 8. Okay, we found at least the number of all possible passwords that we can write, but it is asking us something. It says the password should contain at least 1 digit. Well, okay, then at least 1 digit mean, according to my logical knowledge, at 1, 2, 3, 4, 5, 6, 7, 8. Too much. So if I count that way, right, the number of passwords having 1 digit plus the number of passwords having 2 digits, etc., etc., it would take a while. But how about I calculate number of passwords that include no digits? Right, that's easier. I know the number of all possible. Then if I find the number of passwords that include no digit, then do the necessary subtraction. I would get the number that I'm seeking for. So, number of passwords that contain no digits and are of length 6. Okay, again, the task is to pick 6 digits, right? 6 characters. But this time the characters can be only letters because we don't allow any digits. So 26. 26. Right? 26 to the 6. And similarly, 26 to the 7 for length 7. And 26 to the 8 for length 8. Now, P6, right, the number of passwords that are of length 6 containing characters or digits and having at least 1 digit would be 36 to the 6, 26. Right? Because these are the ones which do not have any digit in it. The rest will have at least 1 digit. I don't care which ones, how many. Right? Make sense? So as you see now, we found P6, P7, and we can just sum them up and we would get P, the number that we are looking for. Do you see like how things can get, like for a simple example like this, the number of steps, the amount of work, right? The level of carefulness, right? So it's like, I highly recommend everyone, like, I don't know, in my opinion, like this is a kind of programming, like, because really requires us to be very careful, not to miss any detail. We don't want to overcount, we don't want to undercount, we don't want to count the exact number of things, right? requires a lot of insight. Definitely, like starting with simple examples, you should practice here, and that will make you very careful CS people. Okay. Yeah, counting is always like it's amazing. It was one of the weakest topics for me. Like I was very bad at it when I was student. Later on, I learned first appreciation of it, and then I made some more progress. Yeah.
What about something possible? Just for example, say you do 10 times 26. Sorry, 10 times 36 to the 5. Could you do that as well? One of them will be a number.
But you see, that is not enough to count all the other ones. No. So the one problem with counting is this: if you don't approach it from the correct angle, you simply get lost, or the calculation becomes really complicated. This is the way that helps us to reach the conclusion easily. But imagine I count it like this. Okay, the number of passwords, since it says at least one, the number of 6 character long passwords that have at least one digit. Oh, sorry, that have one digit. Count this. That's legitimate. Next, according to the definition, it could have 2 digits too. Count them. 3 digits, 4 digits. I don't know, 5, 6, 7, 8. You see, you do 8 subtasks. And if the number that you say is equal to that number, fine, but it's not, definitely not, right? Either that way, or you are going to make an observation. That's why I'm saying this is quite intuitive for CS folks. You will say, okay, if at least one, then if I find the ones which have none and subtract it from the all, then the remainders are the ones that I want. Very, very interesting. After logic, that's one of my favorite topics. Of course, after algorithms too, but so very, very handy. But I don't know. I wish we had more chance to teach. I don't know how they do it in discrete math too, but I would emphasize this more if I were to teach discrete math, for instance, discrete math too. Because really, like, I don't know. There is procedure going on here. If you were to program, definitely you need to think this way. Then, you have to count very carefully, like all these nice, fancy details. Okay, enough. So next rule, called the subtraction rule. So I'm going to borrow the wording from the sum rule. Let's just take this. Almost same wording, but there is a slight change. Okay, if a task can be done in either one way, but are not disjoint anymore. Okay, so there are 2 sets of tasks, let's say ways that you can achieve a task, but imagine some of the ways are shared by the 2 sets. Then the task can be done in N1 plus N2 minus the number of mutual ways. I mean, the most basic example is this counting the cardinality of set union, for instance, 2 sets. So imagine you have a Venn diagram, A and B. So, okay, cardinality of A is N1. Cardinality of B is N2. and A intersection B. You know that it's K. Okay, they share K elements. Then what you would do, like I'm asking you to count, right? You look at here and count the cardinality of A and B. So one way, one simple way, of course, there are many other ways to count, but you can first count number of A, right? The cardinality of A, like the number of elements in A. So you would reach N1. Then count the number of elements in B. And then according to this subtraction rule, count minus K. We know from set theory, you have to take this minus K, right? It has to be this. Because if you don't do this, you will be counting the elements here in this region twice. And that violates the rule of correct counting. You have to count correctly, remember. Right? That's how. But let's do some more CS-oriented example. So number of bit strings that, let's say, 9 of length 9, and that start with 0 and with, sorry, or end with 1 1. Sense? So first, okay, looks like, okay, we are going to consider the, okay, number of strings that start with 0, for instance, but length 9, right? So you could do this, right? Like, and you pick the first one is fixed. So if I ask you how many ways are there to pick the first bit string, of length 9, starting with 0, it is fixed, right? It has to be a 0. So there is only one option for the first. But for the rest, it's like 2, 2, that. So 2 to the 8 such bit strings are possible to write down, right? And next, we could do the same thing, but this time ending with 1. All right, the last 2 is fixed, right? Like you can only pick 1, 1 for the last 2, but for the earlier ones, right? 2, 2, 2 till 2, so 2 to the 7. But we know, we can notice here, we counted, right? Some of these strings end with 1, 1 here, and some of these strings start with 0 here. So we are counting twice, some of them. So now, like in the subtraction rule says, find the ones that start with 0 and end with 1, 1. So, okay, these 3 positions are fixed. So in between, there are 6 positions that we have flexibility. So 2 to the 6. Overall, 2 to the 8 plus 2 to the 7 minus 2 to the 6. Make sense? Good. Okay. So now, okay, let this be enough. I'll do more examples, or that will be, other occasions. But for now, it should be. The last rule is called the division rule. Okay. This tells something like this. There are n over d ways to do a task if it can be done using a procedure which can be carried out in, let's say, n ways, and for each way v among n ways, there are exactly v ways identical to it. Okay, this is really wordy, and I know it generally, that's where I lose so many people, but I learned to come up with easy examples so that I gain everyone back. So division rule is really interesting. Sometimes it sounds dummy, but really very interesting. Okay, imagine the following example. I want to count the number of students here. Okay, one way is obvious, 1, 2, 3, 4, 5, and so on. How about the following indirect way? I want to count the number of eyes and then divide it by 2. But the basic knowledge that I use here, everybody has 2 eyes. I mean, of course, exceptions, etc. But you get my point, right? Or I can count the number of arms. Again, 2 per each person, right? Divided by 2. Reach a number and divide it by 2. Or what else? I mean, like this person example, right? There are many information available to us. We can use it. Instead of counting people directly, I can first count, I don't know, some, let's say, ears, eyes, or of course, I wouldn't like to count the number of air glands, right? Because it would be complicated. I have to pick something appropriate. And we know that there is a function which takes every 2 ears and map them to a person, right? There is this ownership function, right? Ear 1 and ear 2 belongs to person 1. Ear 3 and ear 4 belongs to person. So we don't write that function explicitly, but we know that there is this 2-to-1 relationship between the ears and the people. Every 2 ears belongs to a person. Right? We can elaborate and implement that function. We can do many things with that function as soon as we understand its existence. So this division rule really says something about it. So let me give this. There is this example which has more mathematical nature, so we can then see it. Okay, example. Number of ways to seat 4 people at a round table. Well, okay. First, let us just approach it and imagine, okay, there are 4, around the red table, there are 4 positions. So the first position can be taken by any one of the 4 people who are not seated yet. Makes sense? So then looks like we have, let me say, round table. For the model, I hope it works. So here 4 people can take. 3 people can take here, right? The second position available will be taken by 3 people. Of course, I ignore the fact that maybe this is the second table, then 3 would be here, but, right? Without loss of generality. So the next available seat, I assume it is here and it would be 2 and 1. So it looks like 4 times. So this way of thinking is good, but this problem requires us to be a bit more careful than that. Some of the seatings, although they seem different, but they are indeed same if you consider the people's relative positions or distances with respect to each other. Let me say this. Okay, here is one example. Okay, A sits here, B sits here, C sits here, D sits here. Here, B sits here, A sits here, B sits here, C. As you see in these two seatings, they seem to be different, but indeed they are not. Because every person here, right, the neighbors of every person in these two seatings are same. It's like same idea. Right? Maybe one person looks at from here, maybe this is the scene when I look at from here. So no, I am simply overcounting. So we should then specify when two seatings are identical to each other or equivalent to each other. So we will say two seatings are same, okay, in a sense, or identical, equivalent, all the synonyms can be preferred. When each person has the same left and right neighbors in them. I mean, since there are finitely many elements, if I were to ask you to write a program of it, right, it's easy. Take A and check if it has the both left and right neighbors. Take B and check the same thing, right? C and D. So it's easy to check. Then we conclude that yes, these two are equal to each other, but also not only that, I could continue and create this one here, a third equivalent one, and then I could just do this. So it looks like for one seating, indeed, there are three other equivalent ones to it. And I can find it for every one of these, right? So it looks like this 24 is indeed, 6 group of 4 equal seatings, right? There is a group 1, group 2, group 2, 3, group 6. So then we are going to say, right, 24 divided by 4, which is 6. So there are 6 different seatings, 4 seat ways to see people. But then, yeah, exercise 19, I guess. So can you just compute this for, okay, let's say number of different seatings for 7 people. Still, like the same idea applies, but computation might get a bit trickier, right? For also, we can generalize it to n people. After playing with a few small numbers, then for n people, we can find the number of different ways of different seatings for n people in terms of n. Okay. And you see, like things will go crazy quickly. So many. Counting is a must for us. It makes us aware of the procedures around us, right? We have to see which rule is in action. Generally, the first two is the most critical one: the product rule or the sum rule. The third rule, the subtraction rule, is also called principle of inclusion-exclusion for obvious reasons. And this one also is handy, right? You see, like it helps you not to overcount. Because here, right, in this picture, or if you don't bring, like, okay, we have to be careful because we know in a round table, right, this way of seating and this way, it's still same, right? Here, Yes, in game like card games, for instance, B and D are teams. So it doesn't matter how they sit, right, here or this way or this way. Right? So we should definitely see like what is equal, what is not equal. So quite open, mind opening. So anyways, we are gonna look at this more. Next time we are gonna look at something called principle of pigeonhole principle. Pigeonhole principle. So it's like I don't know if you ever heard, but if there are say 15 pigeonholes and 20 pigeons, obviously there will be at least one pigeonhole which has two or more pigeons in it, because right, 15 of them can take it 111, and for the 16 pigeon, right, 16 pigeon, it has to pick one of the occupied ones, and so on and so on, things like that. Yeah, like counting is great, so we are gonna count more. But that's it for today, and I'll see you on Wednesday. Thank you. Yeah. Generally, yeah. Like, I was just curious. Sure, yeah. Okay, chat room. Have a good day too. Bye bye.